All right, after being done with part A, we can now think about part B. We're going to sort of like replicate the same analysis based on what we just covered here, okay? So almost the same analysis. So essentially, we're going to term by term differentiate and integrate the power series. But before we do that, we have to know everything about the radius of convergence and the interval of convergence. Okay, so for that reason, I'm going to analyze the series for a n equals this whole chunk here, and I'm going to try to apply the ratio test. All right, so limit of the ratio here is equal to minus 1 to the n plus 2, right? N plus 2, x minus 2 to the n plus 1 divided by n plus 1. So instead of dividing all over by the an, which is another fraction, I'm going to flip it over and save some space here. Okay, minus 1 to the n plus 1, x minus 2 to the power of n. All right. Well, this one cancels this one, and we have minus 1 left here, which is not a big deal because I'm taking the absolute value eventually. And this one cancels this, and you're left with x minus 2. Okay. All right, so we can simplify that as, again, minus 1 is not a big deal because it's absorbed and the absolute value. And plus 1, I'm going to isolate x minus 2 from the n parts. And if you pass the limit here for this expression, the limit is going to be 1. You can use the L'Hopital's rule if you want to. And the limit value is going to be x minus 2. Okay, the absolute value of x minus 2. And the ratio test rules that this has to be strictly less than 1. Okay, so now let's try to analyze what this means. Okay, well, this essentially means that x minus 2 is in between 1 and negative 1. And by adding 2 to both sides, to every side, in fact, in inequality, you get 3, and then you got 1 here. Okay? So the interval of convergence is 1 and 3. And the radius of convergence, speaking that the center is 2, so c equals 2. So the radius of convergence is equal to 1, okay, because center is 2 in the interval 1 and 3. And you are far from the end points, just 1 unit, so that makes it the radius of the convergence. All right, so let's see. What I'm going to do next is to figure out how I can differentiate or integrate this series like term by term. But before jumping to that, why don't we just analyze the interval of convergence, analyze the convergence of this series at the endpoints first. Okay, so I'm going to rewrite this series for x equals 1 and x equals 3, and we're going to sort of like check what's going on with the endpoints here. X equals 1, x equals 3. So let's see what we have here. For x equals 1, this is minus 1 to the power of n, right? If you look at this description here, okay? So minus 1 to the n, so let's see, the sum, n from 1 to infinity, minus 1 to the n plus 1, and then for x equals 1, minus 1 to the n, divided by n, right? Right. For x equals 3, this is already minus 1 to the n plus 1. This is already n. Let's see what this x term related. When x equals 3, it's 3 minus 2 to the power of n. So that is 1 to the n, which is exactly equal to 1. Okay, so it's just 1. All right, so nothing carries forward from there. Okay. All right, so let's see what this is exactly. So this is equal to minus 1 to the power of 2n plus 1. You add the exponents. And this is an odd number. Any odd power of negative 1 is negative 1. So that's good news because this series turns out to be minus 1 over n. Another good news is that this is a known series. This is a harmonic series, right? Or it's a P series with P equals 1 and its divergence, okay? All right. How about this one? Well, this is an alternating series with a n being 1 over n. You can immediately apply the alternating series test. Alternating series test, we had plenty of applications of that in the prior sections. And there are two conditions, right? One is that the limit of a n is supposed to be 0, which is the case here, like 1 over n goes to 0. And then 1 over n plus 1 is less than or equal to 1 over n. That makes a n plus 1 less than a n for all n. Obviously, that makes it a n, that makes a n non-increasing. Okay. Two conditions are satisfied, so that this is convergence by the alternating series tests. Okay. So the left end diverges, right end converges. I can go back and touch up this analysis here by saying that I have to include an equality sign here for when I write the interval of convergence here for f. Okay. So now let me just copy f down here, okay, and starting from 1 to infinity minus 1 to the n plus 1, x minus 2 to the power of n, and the interval of convergence is open interval 1 and closed 3. Okay. So now I'm going to do like term by term differentiation. Okay. For f prime. Here we go. And let me just leave it blank for a second. Minus 1 to the n plus 1. When you differentiate x minus 2 to the power of n, so n goes down, and you subtract 1 from the power, but you have another n down there, they're going to cancel out. So you are left with this expression here. And the sum should start from 1 because this is n minus 1. You can't start the sum from 0 because that comes with a negative power for x's, right? That doesn't count, so this is starting from 1. And here, f double prime, and I can tell you that this is going to start from 2. Minus 1 to the n plus 1, n minus 1, x minus 2 to the power of n minus 2. Okay? And then finally, the integral of f. Let me add the integration constant right now. So now I'm going to term by term integrate the power series here. Okay. Minus 1 to the n plus 1, x minus 2 to the n plus 1 divided by n plus 1. Okay. Here I applied the power rule for integration for x minus 2 to the power of n. Okay. So based on this fact here, the interval of convergency, excluding the endpoints for f, okay, is as well the interval of convergency for the derivative and antiderivatives. Okay, so I'm going to go ahead and say that this is 1, 3, 1, 3, 1, 3, and then in every single case, r equals 1, r equals 1, and r equals 1. Okay? So we need to fine tune the endpoints because this whole result here, starting from all the way down, starting from here all the way down, just comes for free from the result I just showed you. What doesn't come out of that result is the endpoints. Okay? So let's just quickly go through this analysis, and I'm going to use a different color here. Okay? Well, first of all, if you plug in 1 or 3 in this expression here, so you will either have minus 1 to the n plus 1 or 3 minus 2, 1 to the n plus 1, which is 1. Okay? So either you have the alternating series, in fact, let me just write it down here. Okay, here we go. Minus 1 to the n plus 1 and minus 1 to the n minus 1 versus minus 1 to the n plus 1 just times 1, right? So what does this add up to? Minus 1 to the power of 2n, which is always coming with even power. So this is equal to 1. So you're talking about series 1. Okay? And starting from, let's say, 1 to infinity. Well, by the n-term test, this diverges, right? Because an, here an is equal to 1, right? And it doesn't go to 0. It doesn't approach 0. So this diverges. Okay, how about this? This is an alternating series with an equals 1. You can immediately apply the alternating series test, and you can show that the first condition fails, which is that the limit of an is 1, which is non-zero. Okay, and therefore this diverges as well. All right, so going back to our analysis here, I don't change anything here because for both endpoints, this series diverges. Okay. Now let's do the similar analysis here, but I can tell you that this case is even more obvious because once you plug in 1 or 3, either you're going to have negative 1 to the n minus 2 or 1 to the n minus 2, which is 1, right? But this time you also have the contribution of n that makes all an going to or approaching infinity. So exact same analysis applies here. So for that reason, I don't change the endpoints for the interval of convergence. Okay. The antiderivative is a different deal, right? Maybe we should analyze that separately. Here we go. So n from 1 to infinity minus 1 to the n plus 1, x minus 2 to the n plus 1, and then n plus 1. Okay, x equals 1, x equals to b. So you have minus 1 to the n plus 1. 1 minus 2 is minus 1, so minus 1 to the n plus 1 divided by n plus 1. And here, I'm using a different color. I hope you don't get confused. When x equals 3, this term is 1, so minus 1 to the n plus 1 and n plus 1. Okay, so let's see what this term looks like. This is minus 1 to the power of 2n plus 2, and that's always 1. Right, because it's an even power. So this series looks like 1 over n plus 1. This one looks like minus 1 to the n plus 1 and n plus 1. Okay. So now we're going to analyze for convergency, but I won't do that. So you're going to pause the video. You will do it by yourself. So this is convergent. And you can use the integral test or the direct comparison test or the limit comparison test. And if you use one of those tests, you should compare this series to the p series 1 over n squared. And p equals 2, it's a p series, it's convergent. Okay. And for this one, you're using the alternating series test. And an, which is 1 over n plus 1, it's converging to 0, plus it's a non-increasing sequence. So it's convergent. Okay. Please pause the video and then convince yourself for both infinite series in terms of their convergencies. Again, in the first one, it's comparison test or the integral test. And the second one, it's the alternating series test. Okay, so since both are convergent, I can go back here and then tune up this, correct it. So here, the interval of convergence is 1 and 3. All right. Well, that ends the analysis for this question. If you have any questions or comments, just send those to my way. Otherwise, I'll see you in another video.